Okay, 11.1, day 2, finding limits analytically. So last class we found limits graphically and numerically. And so now we're going to discover the great way of finding limits analytically. So we're going to look real quickly at how we found the limit of x squared minus 5x plus 2 as x approached 2. Last class, and that is that we set up a table and we plug things into the calculator and we decided, hey, from the left it's approaching -4 and from the right it's approaching -4, so the limit is -4. Well, now, and some of you may have noticed this, we're allowed to solve it analytically, which means algebraically, and you can just plug whatever x is approaching right into f of x. So watch what happens when we find the limit of this quadratic as x is approaching 2. We're just going to plug 2 in for x. So we'll have 4 minus 10, so that's -6, plus 2 is -4. Voila, the same answer. So unless your homework or your assignment or your quiz or your test asks you to find the limit numerically, you can not do the table and plug in x and find the limit analytically. So what about this though? Because you knew there's going to be a catch. If I were to plug 5 in for x in this function, what would I come up against? That's right, this denominator would be 0. So I can't do direct substitution, can I? So we've got to get a little clever. What about the numerator? Can I go ahead and factor the numerator? I'm going to have to push pause, and I will be back in 1 second. Okay, so we're going to be clever, and we're going to factor the numerator. So we'll go ahead and factor out the numerator, finding two numbers that multiply to equal -30, but add to equal a +1, and you got it. And look what happens when we factor out the numerator. When we factor the numerator, we can cancel out x minus 5 and x minus 5. Now our problem turns to finding the limit of x plus 6 as x approaches 5. And we simply do direct substitution. 5 plus 6 is 11. That's our limit. So the interesting thing is that if you plug this into a calculator, or if you graph this function by hand, you would see a hole in the graph when x was equal to 5. But you would see that the value of the graph, f of x, from the right and from the left, is approaching 11, and that's our limit. All right, let's look at this. Once again, there's going to be a problem. If we find the limit of this function as x approaches 3, we do direct substitution, and we're going to have 0 for the denominator, and that's not going to give us an answer. So we look at the numerator. Can we factor? No. We're dealing with a radical in the numerator, and what we're going to do is go ahead and multiply by the conjugate of the numerator that we see, and hopefully you guys remember conjugate from the first semester. That is with a binomial. You rewrite the binomial, but you change the sign in between the two terms. So since we have a minus here, we'll have a plus here. Are we allowed to just multiply a fraction by any value that we want to? Nope. That's why we're going to multiply the denominator by that same conjugate. So it looks like a mess, but you're going to have to trust me here. As we multiply, we're going to be distributing. So the square root of x plus 1 times the square root of x plus 1 is x plus 1, right? And then we're going to have the square root of x plus 1 times 2. So that gives me a +2 square root x plus 1. And you know what's going to happen next, right? When we distribute that -2, and I'm running out of room, so I'm going to put it down here. But those two middle terms cancel out, and that's what conjugates are made for. They get rid of the pesky middle terms. -2 times 2 is a -4. So what's left in the denominator? I'm going to bring that down. We've got an x minus 4 left in the denominator, right? Or I'm sorry, x plus 1 minus a 4. So let's write this out so we can see that those two canceled out. All right, and what about the, that was, I don't know if I was saying denominator, I'm trying to rush and get this done fast. That was the numerator, of course. In the denominator, we're going to go ahead and write this just like this. There's nothing to be gained by distributing conjugate in the denominator. So we're going to go ahead and rewrite the numerator. We know 1 minus 4 is a negative 3, right? So the numerator is going to be x minus 3. And the denominator is the quantity x minus 3 times x plus 1. Oops, shorten that root. X plus 1 plus 2. And I told you we'd be rewarded for not distributing the denominator. X minus 3 and x minus 3 can be, and I should have put the parentheses up here so it was more obvious, they can be canceled out. They can cancel each other out. What are we left with in the numerator? A 1. So now we are finding, it's a new problem, we're finding the limit of 1 over root x plus 1 plus 2 as x approaches 3. So we're just going to do direct substitution. So we'll have 1 over 3 plus 1 is 4, root 4 is 2, 2 plus 2 is 4, and the limit of this function as x approaches 3 is 1/4. Now, there's not a value there. We will see a hole in the graph when x is equal to 3, but a limit does exist there, and the limit is 1/4. Okay, we've got two special trig limits that we have to memorize. The limit of sine x over x as x approaches 0 is equal to 1. You've got to memorize that. Also, the limit of 1 minus cosine x over x as x approaches 0 is 0. But that's it. Those are the only trig limits that we need to memorize. And so what we're going to do is we're going to get crafty and clever and rearrange this problem so that we can use one of those special trig limits. So here we go. Find the limit of tan squared x over x as x approaches 0. I don't see that one of my special trig limits involves tan. So what do you think I'm going to do with tan? That's right, I'm going to rewrite it. Let's go ahead and do the limit of sine squared x over cosine squared x over x as x approaches 0. Can I plug x in? Can I do a direct substitution? Nope. So now let's keep moving because I want to be able to use this one especially. I want to be able to have a sine x over x. So let's go ahead and I'm going to rearrange this. I can write this as sine squared x over cosine squared x times x. I can rewrite that as sine x times sine x over cosine squared x times x. And now I'm just rearranging things, right? I want to get a sine x. I want to get a sine, and see how I'm continuing to write the limit over and over again? We're going to do that because otherwise we're going to forget we're even in a limit problem. So now I'm going to go ahead and rearrange what I have, a legal rearrangement, and I'm going to put sine x over x, okay, so I used up one of my sine x's, times sine x over cosine squared x. Okay, so finally, I'm going to go ahead and rewrite that. It's the same thing. The same thing as saying the limit of sine x over x as x approaches 0 times the limit of sine x over cosine squared x as x approaches 0. And let's use direct, well, we can't use direct instruction here, but we do know the limit of sine x over x as x approaches 0 is equal to 1. So this answer right here is 1. And then we're going to do direct instruction here. So let's see. The limit of sine x as x approaches 0, let's just go ahead and use direct substitution. So sine of 0 over cosine squared of 0. So let's think about this. We're going to bring down the 1. Sine of 0, let's see, at 0, sine is also equal to 0. At 0, cosine is equal to 1, so cosine squared would also be 1. So we've got 1 times 0, so finally the limit is equal to 0. All right. The concepts of calculus are not difficult. The ability to be clever and strategic with our algebra skills is what's difficult. So I want you to probably repeat this problem and slow it down so you can understand how I got from step to step. I was just using algebra. Well, algebra and trig, but actually I didn't use trig until the very end. I was using algebra that whole time. Okay, so here is where they're going to give us our limit answer. So the limit of this function as x approaches c, so some value we don't know, and we don't really care because they gave us our limit, is 5. And the limit of a different function, g of x, as x approaches c, is equal to -2. And this is kind of a goofy little thing that's easy, but kind of too easy. It makes you wonder, really? That's all we do? When we're trying to find this limit, we basically, when we see the limit of f of x, we're going to plug 5 in. When we see the g of x, we're going to plug a -2 in. We could put a plus -2 or -2. And we see the square, we're going to put that in. 5 minus 2 is 3. 3 squared is 9. I know, right? Kind of is doing something totally different than we have been doing. And here, when we see the limit of f of x, we're going to be putting in 5. When we see g of x, we're going to be putting in -2, and we'll carry down that 6. So we've got 6 times 5 is 30 times -2 is -60. So you'll get a little practice with these types in your homework. They're the easiest types. All right, here we have example 5. We have the function of x squared minus 3x over x, and we have the graph that matches, and we're going to be asked questions. So let's find the limit of this function h of x as x approaches -2. So as x approaches -2 from the right, we see that f of x is decreasing and approaching 0. As x is approaching -2 from the left, we see that y is increasing and also approaching. Did I say -2? I'm going too fast. That's a -3 right there. So from both the right and the left, the function is heading towards -3. So the limit is -3. You know what? Okay, I just found the next one, didn't I? So let's stop. I think when I'm trying to rush, I'm making mistakes. So let's go ahead and know that as we're approaching 0 from the right and the left, we are heading to -3. That's our answer to the second one. As x is approaching -2 from the right and the left, let's see what's going on. As we're approaching from the right, we see that the y value is hitting, it's not really a perfect, it's somewhere, well, you know what? You know how my thing elongates things. So for me, it looks like it's a -3, -4. It looks like it's a -4.5. So maybe on your sheet, it looks more like a -4, but I'm going to go with -4.5. So -4.5. And then let's find the limit of this as x approaches 3 from the right and from the left. So as x is approaching 3, y is decreasing and heading to 0 from the right. As we approach 3 from the left, f of x is increasing and heading towards 0. So we do have an answer there. The limit of this function h of x as x approaches 3 is equal to 0. And that's it. Your homework's from the book. And have fun. Thanks for joining me for day 2 of 11.1, Finding Limits Analytically.